Dear students, in this lab we will be demonstrating conservation of energy and conservation of momentum in two parts. Remember how in the very first lab we were doing an experiment with a launcher and a metal ball? In that lab we were focused on the velocities and distances involved. In today's lab we will be doing an experiment that utilizes law of conservation of energy to estimate the muzzle velocity, which is the velocity at which the ball is leaving the launcher. In this experiment we will use the same launcher, a metal ball, a pendulum that is connected to a rotary motion sensor that has a special compartment for the ball. The logic of the experiment is rather simple. As we launch the ball, it's stuck inside the pendulum, which is an example of inelastic collision. The pendulum swings upwards, and the kinetic energy of the ball is converted into the potential energy of the pendulum ball system. We can measure that potential energy by knowing how high the pendulum swings. Now we will use Data Studio to record the rotary motion sensor's data, and we can see the maximum displacement on the graph. As usual, to avoid random errors, we will repeat the experiment to get at least 10 data points. The theta max is all we need from this graph. This is the maximum angle to which the pendulum rotated. Now let's get the data for the two other launching positions. As we insert the ball deeper, the spring compresses more, and so the force exerted on the ball and its exit velocity increase, so the angle should be bigger as well. Now we measure the angular displacement in degrees, but we need height. To calculate the height, we will measure the length of the pendulum from the pivot point to the center of mass. For our analysis, we also need the mass of the pendulum. Alright, this is it for part 1. For part 2, we will be modeling some collisions. We will use a track and cars from lab 2. In this experiment, we will use two motion sensors, one on each side of the track to record each car's velocity. The cars have velcro patches on one side which will make them stick, and magnets on another side to repel each other. In this part we will be observing conservation of the momentum. Before we start, let's get the mass of the carts and also the mass of the load. For part 2a, we'll crash two carts into each other, and one of the carts is almost 3 times heavier than the other because of the load. As you can guess, the heavier cart has smaller change in its momentum and sort of carries through the opposite cart, while the lighter cart will be actually moving in the opposite direction after the impact. In general, this is why heavier cars like trucks are safer to drive, because if they collide with the lighter car, the heavier car will experience less of an impact. These spikes at the start and end of the graph are there because the motion sensors do not work properly when an object is too close to them. This part is where students often have problems. Note how we select specific parts of the plot where the velocity was relatively constant. It's hard to see the mean and standard deviation on the bottom right graph, but you can see the same values on the B graph on the left. We select such a region before and after the collision for each car's velocity graph. So we got V1 initial, V1 final, and V2 initial, V2 final. Notice how one of the graphs shows negative velocity. This is because the cart was moving towards one of the sensors, so the distance was decreasing with time. When doing calculations in the analysis, make sure to pick a proper axis and change the sign of one of these velocities when needed. In inelastic collisions, our v-finals are the same for both cars. In fact, that is the case, and you can use final velocity of one of the cars for both cars since they clearly move together as a system after the collision. The difference in their velocity can be attributed to low number of data points and is pretty much within the margin of the error. Now we repeat the part 2 in 4 other variations according to the manual.